Welcome to the GATE class. So this is Priyanka, working as an assistant professor in EEE department, SC Engineering College. Today my topic is characteristics of DC generator. So first one, we have to know what are the types of characteristics available. So first one is open circuit characteristics, second one internal characteristics, and third one is external characteristics. So before we get into the characteristics, why these characteristics are very important. So in order to find what will be the consequences in voltage or current, so for this we need to find out what are the essential of characteristics in DC generator. The first one, which helps to determine the voltage regulation. Second one, which is used in designing the field control. And third one, which is help to identify the critical resistance and speed. And last, we have to select the type of generator. Depends upon the applications we have to use it. Okay, there are four types of essential requirements for the characteristics of DC generator. The first one, which is helps to determine the voltage regulation. Second one, it helps in designing field control, and third one, which helps to help identify the critical resistance and speed, and fourth one, depends upon the application, we are able to know what kind of generator we can use it. So next one, what is meant by armature reaction? So this is one of the important criteria for the characteristics of DC generator. So first one, what is meant by armature reaction? So it has two windings, field winding and armature winding. So they are about to take some reactions between these two windings. So that is called as armature reaction. So the first one, when a DC machine runs, current flows in the armature conductor. So the current will be flows in both field winding and armature winding. So field winding, we can say it is a main winding, some kind of voltage in the armature also. So this armature which is about to infer with the main winding. So this collaboration or this disturbance, we can say it as an armature reaction. So this armature current produces its own magnetic field. So due to this own magnetic field, there will be some kind of armature voltage will be produced in the armature winding. So this armature winding which is about to disturb the main winding. So because both are in opposite direction, so the disturbance we can say it as an armature reaction. This is also one kind of drop or loss in a DC generator. So second, this is the circuit diagram of armature reaction DC machine. So this one is main winding and this one is field winding. So already the field winding has the main winding. Due to its own magnetic fields, the field winding which is about to cause some disturbances. So almost the way will be some disturbance associated with this. So distortion, we can say it as what? Armature reaction. So next one, there are two kinds of field. One is main field and other one is armature field. So main field which is about to produce only by the field winding. There is the armature field, it consists of armature current. So this armature field is about to disturb the main field. So that is called as armature reaction. So when load increases, the armature currents is about to increase, so that armature reaction is going to be very stronger. Therefore the loss will be very high. And next one, three types of characteristics. The first one is open circuit characteristics. In open circuit characteristics, we are not about to connect any kind of load. So we are taking as it is. So this is called field winding and this one is armature winding. So this both are connected in parallel. So what is mean by open circuit characteristics? So here we are not about to connect any kind of load in it. Okay, so that one we can say it as no load saturation characteristics, because we are not connected any kind of load. So that is no load characteristics. So we are about to find the characteristics between no load EMF and field current. So the field current, as usual, it's going to be passes into the generator, but we don't connected any load. So that is why we can say it as what? E naught. So this is the characteristics. Here the characteristics are drawn between field current and the no load voltage. So if you keep on increasing the field current, the voltage is about to increase and certain point it's going to be saturated. Though you increase the field current, the voltage won't be increased because it reaches its rated voltage. So it won't increase after that if you keep on increasing the field current. So this open, the data of OCC, open circuit current, is obtained by the generator at no load speed at the rated constant speed. So if you connected any load only, the speed will be vary. Here we not connected any load, therefore the speed won't be changes. So the field current is gradually increased according to the voltage what we have recorded in the generator. So the connection arrangement is obtained as per the figure what we have seen before. So again the generator can be divided into two, series, shunt and compound. We will be see later. And this from the equation EG. So the generator EMF is equal to K flux. So whatever the voltage produced which is equivalent to flux. So there won't be any losses in it because we have not connected any load. Once we connected load only, you will be finding this armature reaction drop and the voltage drop and all. So next one, so it initially induced EMF with some kind of residual magnetism. So residual magnetism nothing but due to this armature current passes into the armature field, so there will be some own residual flux. So it is able to produce some voltage. So that we can say it as a residual magnetism. Therefore, that is why the graph will not started with a zero. It has some minimum voltage it will start due to its own residual flux. And next one, external characteristics. So obviously external characteristics is about to do with some load characteristics. So the external characteristics curve show relation between the voltage and the current, because here we have load has been connected. So the terminal voltage is less than the generated EMF. Why? Because this terminal voltage will not be equivalent to the generated, because here we have connected the load. Once you connected the load only, you will be having two types of losses. One is armature drop, another one is voltage drop. So this two drops are going to be occurred in that, so that this generated EMF which is not equivalent to the terminal voltage what we have given. So the external characteristics are very important in order to find the sustainability of the DC generator. So therefore this type of characteristics we can say it as a performance characteristics. So once it started performing for the given load and all those things, so that is why we can say it as a performance load. So this is the characteristic of separately excited DC generator. So here we have connected the load. So look at here, it also connected with the load current from with the no load voltage, generator voltage and terminal voltage. So we can say it as at the initial it will be very saturate, okay, which means it is a constant value. But once you keep on giving the load, as I told you, you will be having two types of load. One is armature reaction and one is voltage drop. So according to that, the straight curve will start decreasing due to this voltage drop. So before that, we don't have any kind of losses in the internal characteristics, therefore it will be in a saturation region. But here we have connected the load, so obviously we will be having some losses, that is called as armature reaction drop and voltage drop. So automatically the graph shows decreasing in it. So DC, so if there is no armature reaction and constant, the current will be same. But if you have this kind of loads in it, automatically it's going to be decreased. So these are the characteristics of this generator. So this one is called shunt generator. Shunt generator, shunt in the sense parallel. Here the field winding and armature winding are connected in a parallel manner. So the characteristics of DC shunt generator, so you will be having both internal and external characteristics. So we need to calculate before we giving the load what will be the generated EMF. Once we given the load, what will be the generated EMF. So to build up voltage of the shunt generator, the generator is driven at the rated speed. So at initially it should be started with the rated speed and then it gradually decreases once you connected the load. So the initial voltage is induced due to the residual magnetism. So it has its own magnetic field in order to produce a minimum voltage, not start with the zero. It will have a minimum voltage, it will start. So the generator builds as usual the open circuit characteristics. Once you given the load, it will be going for the external characteristics, which means the external characteristics. So this is called DC shunt generator. So you will be having here connected with the loads. So here we will be having two types of characteristics in order to find both open characteristics and internal characteristics. Okay. So in internal characteristics, you are not connected with any load, so that the graph will be same as constant. But though it has armature reaction. So we have an armature reaction, so that what will happen? So you will be having some losses, but comparatively characteristics loss is very less. But if you go for the external characteristics, obviously the losses will be very high. The load connector, therefore you will be having a voltage drop and all those things. So automatically which is going to be reduced. And next one, this is called characteristics. So during a normal running condition, when the load is increased, the load current obviously increases because the current and resistance proportional. Therefore, if you increase the current, obviously the resistance is going to be reduced. This is how it shows. So we go for decreasing the load resistance because the voltage is going to start to flow. So the load resistance can be increased up to a certain limit. After that, you can gradually increase it in order to reduce the I square R losses. So characteristics of DC generator, beyond its limit, any further decrease in the load resistance results in decreasing the load current. So it obviously going to be turns back and with the dotted line. So So this is the characteristics of DC series generator. So series generator is nothing but the field winding and the armature winding are going to be connected in a series manner. So it shows the same kind of thing. So you can compare the series generator with the open circuit characteristics. As usual, you will be having a minimum current of voltage due to its over residual magnetism. So load current, if you given a load current, obviously that according to that the voltage levels are going to be decreases. Here also will be having some armature reaction drop, voltage drop, automatically the loss is going to be bit high. So this is the DC generator field winding. Here the field winding which is equal to the load current. So this is called compound generator. So compound generator, which is nothing but the combination of both shunt and series generator, we can say it as a compound generator. So in compound generator we have three types. One is flat component, other than under component and over component. So the graph has been shown in the type of this. So this also we are about to find with the help of load current and the terminal voltage. So automatically it is about to decrease its over. So it is the AC is the flattered one, which means it is the rated. So over component in the sense the voltage will be very high, therefore it reaches more than C. Under in the sense it's about to, the loss is going to be very high, therefore the voltage is going to be less. So which is about to, AD will be lesser than the AC. We go for this problem. The first one, a 200 volt 10 kilowatt lap winder DC generator has 10 poles and 500 conductor on its armature. If the pole faces 80% of the pole pitch, the pole pitch conductors required for the fully compensated armature reaction will be dash of conductor pole. So we have to find what kind of the conductors and poles will be there. The first one, generator rating. So generator rating is 200 voltage level at 10 kilowatts. Second one, lap winding DC generator. Number of poles will be 10. Number of armature conductors will be 500 and the pole percentage is 80%. Here we have to know what will be the conductor under each pole pitch. So the formula is about pole phase coverage divided by 100 into Z by P. So we know that Z is the number of conductor, armature conductor, so that is 500, and P we know, which is nothing but number of poles. Since it is a lap winding, so A is equal to P, so that P is equal to 100. So if you substitute 0.8 into 500 divided by 10 into 0.8, so you will be getting 0.8 into 50, you will be having 40. So the answer will be, so the answer of the armature conductors required per pole to fully compensated for armature reaction is 40 conductors per pole. So they have given the pole coverage and the armature conductors, and they have given the lap winding number of parallel paths is equal to 10. So with this three inputs, we are about to find what the conductors. Okay. So for that the formula is pole phase coverage divided by 100 into Z by P. So we know that 80%, so 80 divided by 100 is equal to 0.8, that we have mentioned it, into Z number of armature conductors 500, and we know P is equal to number of poles. Since it is a lap winding, so A is equal to number of poles, which is nothing but 10. So if you substitute that, you will be getting what? 40. So you need to be, for the armature fully compensated, your conductor per pole will be 40. And next one, calculate the magnetic flux per pole of a 6-pole DC generator with a 240 wave connected armature conductors operated in an open circuit voltage of 500 volts while operating at 1000 RPM. Here they have given what speed, voltage, what kind of pole, and the wave connected. Here about to find what is that magnetic flux. So we are about to find what? Phi, we have to find it. So we know the formula is equal to P into 5 into Z into N divided by 60 into A. We know P is equal to number of poles, Phi is equal to flux, Z is equal to number of conductors, N is equal to speed, and 60 divided by A. So we know A is nothing but number of parallel paths. So here they have given a wave connector, therefore A is equal to 2 by default. So you substitute all those things. So we know E is equal to 500 into, so number of poles is equal to 6. What input we have to find it? 5. So into Z is equal to 240, speed is equal to 1000 divided by 60 into 2. So you will be getting 5 is equal to 0.04 167 Weber. Okay, so this is going to be the flux. So we know generated EMF, we know number of poles, we know number of armature conductors, we know in speed and armature. Okay, number of parallel parts. So if you substitute here, we will be finding the phi. So therefore the phi is equal to 0.04167 Weber. And next one, a 4-pole separately excited wave connected DC machine with negligible armature resistance is rated for 230 volt and 5 kilowatt at the rated speed of 1200 rpm. If the same armature coils are reconnected in the lap winding, what will be the rated voltage? So they have given like the wave connector we are about to shift it into the lap. At that time, what will be the voltage and power? So here the voltage will be 230, power will be 5 kilowatts, speed will be 1200, poles will be 4, armature resistance is just going to be negligible. The value will be very low, so you can neglect it. So here we know wave winding always 2, A is equal to 2, for lap winding A is equal to P. So DC machine, we know the EMF equation E is equal to phi into P into Z into N divided by 60 divided by A. So E is nothing but generated EMF, P is equal to number of poles, phi is equal to flux, Z is equal to total number of armature currents, N is equal to speed and A is equal to number of parallel paths. Here we are about to connect a wave connected into the lap winding. So next one, compare the number of parallel paths. For a wave winding, obviously A is equal to 2, whereas in lap winding A is equal to P, that is nothing but 4. Okay, so we have to relate the lap and the wave winding. So this is a very important formula in order to change the wave into the lap. So first, E lap is equal to B wave is equal to A wave into A lap. Okay, E nothing but voltage and A is nothing but number of lap winding. So here the wave we are about to connect it into the lap. Therefore, E lap is equal to E wave into A wave divided by AP. So we know the rated voltage is 230 into A wave is nothing but always 2. A is equal to 2. So we are substituted into 2 and we know A lap is equal to number of parallel paths. So in this A lap, number of parallel paths will be 4. Therefore, substitute 4. So if you divide this into, we will be getting 115. So obviously we can know here, if we connected lap winding into the wave winding into the lap winding, the voltage is going to be divided. So 230 will be divided into 2. So that is why we got 115. And what about the power? Okay, so for the power we have to find with some help of formulas. Okay, so we know the power and we know what? Current. Okay, we have to find power. So available total armature scales with the number of parallel paths is equal to I lap is equal to I wave into A 4 by 2. So it is a reverse of wave. So 4 by 2. So we know 2 into I. So we have to find, we know power is equal to 5 kilowatts. So therefore 5000 divided by 230 will be getting 21. So we need to multiply into 2. Therefore we will be getting 43.7. So if you multiply with this, okay, so the power is equal to B into Y. B we know that very well, 115, because we find out in the last step. Okay, so now we have found out the current 43.478. So if you multiply with, we will be getting 5. So therefore there won't any changes in the power, will be having only the changes with the voltage. For this problem, the voltage is equal to 115 and therefore the power is equal to 5 kilowatt. So this is one of the important problem in a gate. Is equal to 115 and the power is equal to 5 kilowatt. Thanks, we'll be continuing in the next class.